So hello and welcome back to Level 3 NCEA Physics and a new external standard, electrical systems. And to begin with electrical systems, let's first look at the concept of electrical current. So in terms of current, the first thing we have to do is quantify the concept of charge. So the symbol for charge is Q, and the units are coulombs, which has the symbol of capital C. So the charge on one electron is known as the elementary charge, and it's 1.6 times 10 to the negative 19 coulombs. And therefore, how many electrons are going to be in 1 coulomb? Well, there'll be 1 coulomb times 1 electron divided by the elementary charge. So about 6.25 times 10 to the 18 electrons in 1 coulomb of charge. Quite a number. So current is essentially the rate at which charges move through a conductor. Using the analogy potentially of rivers, it's the flow of electrons as opposed to the flow of water. So the symbol is capital I, and it is measured in amperes. With the symbol or the unit of the amp or capital A. Okay, so it's contracted down to the term amp. And exactly what is an ampere? Well, essentially an ampere is the amount of coulombs passing by a particular point per second. Okay, so it's just basically coulombs per second. Okay, the rate of flow of the electrons. So why is it that electrons flow instead of protons and neutrons from at least a physics perspective, not necessarily a chemistry perspective? Essentially the reason why is that the outsides of an atom are where the electrons lie, and it's easier to pull the electrons off the outside of an atom than it is to pull the protons and neutrons out, which are in the nucleus, and have that strong nuclear force as opposed to just the electrostatic attraction of the electrons to the nucleus. So that's why electrons flow instead of the protons and the neutrons. In this course also, we'll be looking at circuit development. Okay, so you have to be familiar with the following circuit diagrams. A good way to do it is look up Kung Fu circuits on YouTube and practice that every day. So in terms of current, this might be kind of against common sense, but there is electrical current and conventional current. So conventional current is when you're drawing a circuit, you always show the current flowing from positive to negative. Okay, we make the assumption in the 1850s, we got it wrong, that the charge carrier was positive. So that means the charge carrier goes from positive to negative in conventional current. Okay, which is the opposite of what the reality is of electrical current or electron flow, which goes from negative to positive. So it's a little trick that sometimes trips people up. We'll be using conventional current or positive to negative, not electronic or electron flow, which goes the opposite direction. Just be careful with that. So the first law I'd like to introduce to you is Kirchhoff's first law. And essentially it just states that the total current coming into a junction must equal the total current leaving this junction. Okay, so for the first example, on the left, 5 amps is coming in, saying you've got 3 amps on one of the tributaries of the junction, so therefore it must be 2 amps on the other tributary. And on the right hand side, you'll notice that it's 9 amps coming out of the junction when 5 amps goes in. So it just means that there's 4 amps going in the opposite direction than the 9 amp tributary. Okay, so to summarize that, the sum of the currents in a junction equals 0. Okay, so if it's entering the junction, it's a positive, and if it's exiting the junction, it is a negative. Okay, it's the reason why we got the results we did in the previous example. And that is all we need to look at today in terms of electrical current.